Well, welcome everyone to the Electrical and Computer Engineering Distinguished Lecture Series. So this is the second lecture of the year, Professor Vincent Poor from Princeton, and you have here the slide. We will have another one in February, then in April, and the last one in May. So thank you for coming, and I hope you come also to the next ones. So it's a pleasure for me to introduce Professor H. Vincent Poor. Professor Poor is the Michael Henry Strater Professor of Electrical Engineering at Princeton University, and he's also the Dean in the School of Engineering and Applied Science at Princeton. His research interests are in the area of wireless communications and networking, application of statistical signal processing and stochastic analysis in many fields, not just communications, but for example also finance. And it is really remarkable that in addition to being dean, he's really very active in research with a very big group and very active in the community. Professor Poor got his PhD in electrical engineering and computer science from Princeton University in 1977, and he came back to Princeton in 1990 as a faculty. Between 1977 and 1990, he was at Urbana-Champaign, and he has held many visiting positions in different universities all around the world. His career is very distinguished. Professor Poor is a member of the National Academy of Engineering. He's also a member of the National Academy of Sciences. He's a fellow of IEEE, of the American Academy of Arts and Sciences, of the Royal Academy of Engineering of the United Kingdom, of the Optical Society of America, of the Institute of Mathematics and Statistics, and many others. He also holds an honorary doctorate from the University of Edinburgh, and he has served as president of the IEEE Information Theory Society and as an editor-in-chief of IEEE Transactions of Information Theory, which is the main publication of the IEEE Information Theory Society. He has also received the IEEE Education Medal, and his work has been recognized in many occasions with the most prestigious awards in the fields of information theory, communications, and signal processing. So it's an honor for us to have Professor Poor here today, and I ask you to join me in welcoming him here.
Thank you. Good afternoon. Thank you, Javier, for that very nice introduction. I really appreciate it. Well, it's an honor to be here. I saw the other speakers in this series, and they're really quite a distinguished group. Can everyone hear me okay in the back? Is that okay? It's a very distinguished group, and I'm honored to be on the same page with them, as it were. Thank you for coming. I know it's a rainy day, so I appreciate you coming out of your warm, dry places into the rain to get over here, but I really appreciate it. So today, I'm going to talk about wireless networks. As Javier mentioned, this is a field that primarily the field that I've been working in the last 2 decades or so. And the title of this talk is a bit contrived in the sense that I really had 4 things I wanted to talk about, and 4 different areas of research that we've been involved with in my group at Princeton. And I looked for a title that would cover the 4 things. And this is the title that I came up with, and I'll explain in a minute why it does that trick. So just start out with a little bit of a, maybe I'll back up just a second and just remind you, since not everyone in here is from this field, that wireless technology is one of the most advanced technologies of our era, and one of the most rapidly advancing. There's still a tremendous amount of research activity in this field, a lot of development activity. The UN has estimated that there are almost 5 billion cellular subscriptions in the world, and this is in a population of 7 billion people. So the market penetration of this technology, which is really only about 25 years old, at least in its modern form, is really astonishing in a way. So it's a very interesting field to work in. There's a lot of dimensions to it, and I'm going to talk, as I said, about 4 particular research areas that we've been interested in recently. just to give you a sense of some of the things that are going on in this area. Now, I'm going to use some, I'm an engineer, so I'm going to have to use some acronyms. And I wanted to put up this slide just for the benefit of those who maybe aren't in this field, just to give you an idea of a principle in wireless that, or in all communication networks, called layering. Now, engineers, for the purpose of designing networks and operating them, tend to divide them up into layers. In wireless, the principal layers are the ones that are shown here. The application layer, which is the layer at which we interact with the network, say web browsing or talking on the phone or something like that. And then there's the network layer, which is responsible for getting messages from point A to point B. So if I call you on your cell phone, the networking layer is going to route that call around through a network to wherever you are. Then at the bottom, there's the physical layer, which is the actual medium of communication. And for wireless, that is the ether. That is, wireless is radio, based on radio transmission. And then there's a layer between the networking layer and the physical layer called the medium access control layer, which just schedules messages on and off the physical layer. So it takes messages out of the sort of logical space of the network and puts them in and out of the actual physical medium. Okay, so I just want to mention that. This is well known to people in this field, but just to give you a sense of what some of these things mean when I bring them up later. So now, having set the stage a little bit, I want to say something about wireless research over the past 25 years. So we have, wireless is an old technology. It goes back to the 19th century. The earliest wireless systems were telegraph systems. Marconi's name is associated with that. And there's sort of a classical era of wireless, which is the era of Marconi, the telegraph, the radio, television, and so forth. And then there's a modern era of wireless, which we're living in today, which is the era of Wi-Fi, the cell phone, and so forth. And this modern era is about 25 years old. And a lot of the modern era of wireless has been driven by, in terms of research anyway, has been driven by developments in the so-called physical layer, that is, having to do with wireless data transmission over the air. And these are all a bunch of acronyms that I'm not going to describe in detail, but these are just some of the main developments. These acronyms stand for some of the main developments in the wireless physical layer, ways of transporting data across the physical layer. These have all been major developments that have punctuated the development of the devices that we're used to today, our cell phones and so forth. More recently, so this is really about the physical layer, that is the physical wireless medium, but more recently, research in this area has started focusing, instead of on the physical layer, it started focusing on the interactions among various terminals or nodes in the network. So rather than looking at only at data transport, say between your cell phone and another receiver, it's looked at how nodes work together in various ways. And so in that context, there are various modes of interaction that have been examined. Competition between nodes for resources, like the radio spectrum. Collaboration, which is a big part of modern and emerging wireless systems, is collaborative and cooperative communications, and so forth. Now, there's been another focus, which is optimization across layers. So the layers, or networks are designed using layers because it allows for evolution of networks to progress efficiently. So, for example, the internet is a classic example of a layered network. If you didn't have layering, then anytime you install the new web browser on your computer, which is sort of at the application layer, you would have to then change the whole network. That is, all the way down to the fiber optics, the switches, and everything would have to be changed in order, if you didn't have layering. So layering allows you to modify parts of the network without having to redesign the whole network. So layering is important, but in the case of wireless networks, the physical layer is much more prevalent in the performance of the network than it is in, say, the internet, where you primarily are using fiber optics to transport data, which is a very stable type of medium. So there's been a lot of interest in wireless networking in optimizing or looking at interactions across layers. So that is, how does the physical layer interact with the medium access control, or how does it interact with the routing or even the application? This is a big area of research today. Some of the students I met today are working on this here at Delaware. And today I'm going to sort of talk about things that relate to the interaction, or at least relate to the two layers, the application layer, again, that's where we as humans interact with the network, and the physical layer, which is the layer of data transport. And the main two applications of wireless networks are information transmission, like sending movies or phone calls or whatever across the network, or statistical inference, that is making, gleaning information from things that you measure on the network. And so that's the sort of the genesis of the title of this talk, is that I'm going to look at four things, all of which are sort of motivated by these applications of information and inference, but they're problems that come up in the wireless physical layer. And so that's why, hence the title. Okay, and these are the four things I'm going to talk about. So the first one I'm going to talk about is so-called physical layer security in communication networks, and this is motivated by the application of secure information transmission. Then I'm going to talk about distributed learning, and this is motivated by inference in sensor networks. Then I'm going to talk about a problem called finite block length capacity, and I'll elaborate on all these as we go along. This is motivated by the transmission of multimedia information, multimedia meaning things like voice, images, and video. And then I'm going to talk about message delivery in small world networks, and this is motivated by social networking. And social networking is an application. The applications of social networking are both information sharing and inference, that is learning about the environment. So this sort of satisfies both aspects of the title. So let me just start right away with this first topic, physical layer security in communication networks, and this is again motivated by the application of secure data transmission, and much of what I'm going to talk about today is joint work with two people, Yingbin Liang, who was a postdoc at Princeton, now she's at Syracuse, and Shlomo Shammai, who's a colleague at the Technion, and others whose names I'll mention as we go through this. So just by way of motivation, let me mention very important developments in one of the very important developments in the modern wireless era, which was a recognition that the physics of the radio channel could be exploited to increase the capacity and reliability of wireless transmission. So when I was a student long ago, we always felt that the physical properties of the radio channel were detriments to providing high capacity, high reliability data transmission. That is, they were our enemies in this game. But we learned in the 90s, surprisingly, that in fact, one of the particular properties of the radio channel, namely fading, can be exploited and used to increase capacity and increase reliability. So this is a revelation leading to so-called MIMO systems, multiple input, multiple output systems, meaning there are multiple antennas on both transmitter and receiver. And every modern standard today that we use, cell phones, Wi-Fi, all other wireless systems today use this principle. Okay, so that's how we get increased capacity in wireless networks today, is largely by using this principle. More recently, this same principle has been put to use in using systems, so-called cooperative communication systems and relaying systems, which are basically loose forms of multiple antenna systems where the multiple antennas are actually deployed on different terminals. But it's basically the same principle. There's another development, actually even more recent, cognitive radio, which takes advantage of other physical properties of the wireless medium to get additional capacity. So for capacity and reliability, we already know from recent history that the physical layer can provide for us. So what about security? Now security, of course, we all know is a very important aspect of communication. You know, if you look at the news of the world, scandal in Britain, clear that you know, there's some security lapses in the cellular network. Now those aren't the kind I'm going to talk about today, but certainly security is paramount in our communications, and we certainly don't want to be using an insecure communication system for our banking or for any other purposes. So security, and here I really mean data confidentiality, has traditionally been a higher layer issue in wireless networking. That is, it's been something that's been done at the application layer rather than at the physical layer. And usually the method of securing data transmission is encryption. So you encrypt with a secret key, send the message over the air, and it's decrypted at the other end. Now, encryption is good for certain types of networks, but there are emerging types of networks where encryption is not a good solution. So, for example, one type of network that is increasingly found is an ad hoc network or a peer-to-peer network where communication goes on from terminal to terminal directly rather than through a network with an access point. Okay? So in this kind of network, it's very difficult to manage the key distribution in a proper way. Also, in other networks, for example, sensor networks, I'm going to talk a bit more about that later, another type of encryption, public key encryption, which can be used without much infrastructure, is also not practical because the terminals in a sensor network are very unsophisticated. That is, they don't have a lot of computational power, and that means that it's very hard to run sophisticated encryption algorithms like public key cryptography needs. So the traditional solution for providing data confidentiality in networks aren't practical for certain types of emerging networks. So for this reason, there's been a lot of interest in the last few years in looking at ways in which the physical layer, that is the physics of the radio channel, might be able to provide security, just like it can provide capacity and reliability. And the underlying fundamental science here is called Information Theoretic Security. You'll see why in a minute. And this is basically a way of using mathematics to study the ability of the wireless physical layer or any other communications medium to provide security of communications. So let me just say a little bit about another way to look at physical layer security is to think about security as a type of coding. So traditionally we have a source, Alice, say, would like to send a message to Bob, and keeping it secret from an eavesdropper, Eve. Okay? And the way a traditional system would handle that is there'd be an encryption system. So we might call it a security encoding system. And then there'd be an ordinary communication system, which is would involve the wireless medium or channel. And in order to take care of impairments in this channel, there'd be a reliability coder, so-called error control codes. So we'd encrypt with a secret key. The encrypted data would be error control coded, transmitted through the channel. The eavesdropper could undo the error control coding, but it wouldn't know the key, so couldn't undo the encryption. And then this would be undone at the other end, and Bob would get the message in confidence. Now, another way of doing this would be to forget about separating these two functions and just to build a single encoder, a secure encoder that could take advantage of the physics in here to do both error protection and security, provide both error protection and security. So this is, those of you who are familiar with wireless systems know that, for example, in multimedia transmission, we do the same thing with source coding or compression and channel coding. We do joint source and channel coding. Well, this is the same thing. We're going to do joint security and channel coding, basically. So that's another way to think about physical layer security. It's just a way of reducing complexity of the system by using a single encoder for both tasks. So let me just very briefly mention the history of this problem. Like everything else in information theory, it goes back to Shannon, or almost everything else in information theory. It goes back to Claude Shannon. And in 1949, Shannon published a paper in the Bell System Technical Journal looking at the looking at the secrecy of encryption systems, so-called cipher systems, in an information theoretic setting. That is, he used information theory to prove that cipher systems could be perfectly secure from a theoretical point of view. And Shannon, in doing this, Shannon had good news and bad news. Okay? The good news that Shannon had was that cipher systems can be perfectly secure from an information theoretic point of view. That is, you can design a system so that an eavesdropper can't obtain any information about the secret message. The bad news is that for that to happen, the key has to have the same entropy, or at least the same entropy, as the source that you want to transmit. That is, it has to have as much randomness in it as the source did, meaning that it takes just as much resources to transmit the key as it would in secret to the receiver as it would have to transmit the source originally. So it's sort of good news, bad news. Now, for the 1940s, this wasn't really bad news because the key in the 1940s was something you transported in a briefcase, handcuffed to the hand of a guard from Washington to London, say. And so you had another channel to transmit the key. And then once you had the key in London, you could then have a secret, Churchill and Roosevelt could have a secret phone conversation in private. Well, in a wireless network, this is not very good, right? Because in a wireless network, you've got to use the same physical resources to transmit the key that you do to transmit the source. So that falls heavily on the side of the bad news in this particular piece of work. Now, if we can zoom forward about 25 years, and Aaron Weiner, also working at Bell Labs, was the first to look at the idea that the physical medium of transmission itself might be able to provide security. So he proposed what he called the wiretap channel, which is a channel with a source, a legitimate receiver, and a wiretapper. So he used the term wiretapper because he was interested in telephone network, not wireless. The idea is the source has a message, W, that he or she would like to send to the legitimate receiver with reliability while keeping it secret from the wiretapper. And he proposed a formalism for this based on Shannon's notion of channel capacity, that is reliable rate of transmission, and the second term, the so-called equivocation, which is just the conditional entropy of the source at the wiretapper's receiver. It's written there. And he showed also good news and bad news. Okay, Weiner's good news was that you can, in fact, transmit in perfect secrecy in such a configuration without resorting to a secret key. Okay, that is, the channel itself can provide perfect secrecy of transmission. The bad news was that in order for that to happen, the wiretapper has to be degraded, so-called degraded relative to the legitimate receiver. That is, the wiretapper's measurements have to be sort of a noisy version of the measurements at the legitimate receiver. Okay, so it's hard to guarantee that in practice, so this is largely of theoretical interest, but it's a very considerable theoretical interest because it points to a potential resource for providing security. So just maybe zoom forward a little bit more. Also in the 70s, there was another important piece of work that turns out to have been very important for the application of these ideas in wireless. And that's the so-called broadcast channel with confidential messages. So a broadcast channel is a channel where there's one transmitter and multiple receivers. Okay, so like a television network is a broadcast channel. So in the broadcast channel with confidential messages, there are actually two messages. One of them, W0, which is destined for both, is intended for both receivers. So that's a broadcast message. There's another message, W1, that's intended only for receiver 1 and should be kept secret from receiver 2. So with respect to W0, this is a broadcast channel. With respect to W1, it's a wiretap channel. And Chisar and Kerner studied this channel, again, not for the sort of wireless case, so-called discrete memoryless case, and they generalized Weiner's result to this channel. Okay, so now we can zoom forward another 30 years to almost the present, when, for the reasons I mentioned earlier, the research community got to be interested in this idea of using the channel to provide security in the context of wireless networks. And so in the last 5 years, there's been a lot of research in this area. And I want to mention a couple of results here, and then I'll just give some broad thoughts about the area. But one of them is work with Yingbin and Shlomo, who I mentioned earlier, which looks at this model, the BCC model, but for a situation where the links between the source and the receivers are wireless links. So either they're corrupted by Gaussian noise, or they're corrupted by Gaussian noise and fading. That is, the links are fading. That is, the signal amplitude is fading in and out over time. Remember, that's what gives us capacity with MIMO systems. So this is an important aspect of the physics of radio channels. And in a paper, these are papers, by the way, IT here means the IEEE Transactions on Information Theory, which Javier mentioned earlier. So you'll see that a lot in this talk. And for these channels, we were able to determine the so-called secrecy capacity region, which is the region of rates at which this message, W0, can be sent reliably to both receivers, and W1 can be sent reliably to receiver 1 and in perfect secrecy from receiver 2. And I'm not going to give you any formulas, but I'll just show you with some examples what happens. So this is showing that region. This is along the horizontal axis. This is the rate of the common message. Along the vertical axis, this is the rate of the secret message. This is a case where the signal-to-noise ratio at receiver 1 is 10 dB, and at receiver 2 it's 5 dB. And the red region, the red line is the outer region, outer boundary of the capacity region. So everything under this is achievable without a secrecy constraint. That is, this is the set of rates down here that we could send these two messages to their intended receivers without worrying about secrecy. And the blue dash line is the outer boundary of the secrecy capacity region. That is, it's the region the region of rates over which we can transmit the messages reliably and in secret as needed. And you can see that when we impose secrecy, there's a loss in capacity for the secret message. And that's because this additional capacity, which is still out there, has to be used to confuse the secondary receiver about the secret message. And I'm not going to get into that, but that's part of the way these systems work. Now, this is a case where we do have a degraded secondary receiver. The signal-to-noise ratio is lower at the second receiver than the first receiver. Now, if we change that signal-to-noise ratio, keep the first receiver at 10 dB, change that signal-to-noise ratio, you can see as that secondary receiver's signal-to-noise ratio gets smaller, the range of common rates shrinks, and the range of secret rates enlarges. Okay? And that's just because the common message has to be sent to both receivers, so if the secondary receiver gets worse, the quality gets worse at that receiver, you just can't transmit it at as high a rate. It's a bottleneck for that message. And then as that receiver gets worse, it's easier to confuse it about the secret message, so the range of secret rates gets broader. But one thing that you don't see here is the case where both receivers have the same quality. That is, there's no case where the secondary receiver signal-to-noise ratio is also 10 dB. And that's because at that point, the secrecy capacity region collapses. There's no way to transmit in perfect secrecy in this situation. And that goes back to Weiner's bad news, which is that you need a degraded eavesdropper in order to get perfect secrecy on the other link. So let's look at the fading case, because if this were all there were, I wouldn't be talking about this. Now this is the same situation where we now have fading on the two links from the broadcast links from the source of the two channels, two receivers. This is the case with so-called Rayleigh fading, where the gain of the links has this exponential distribution. Now we're looking at the case where both receivers have the same noise level, but the link to receiver 1 has the Rayleigh fading with unit parameter, and the link to receiver 2 has Rayleigh fading with parameter sigma 2. So those of you who aren't in this field, Rayleigh fading is a standard model for radio fading. And as sigma 2 gets smaller, this parameter, the fading becomes more intense on receiver 2's link. So that's worse for receiver 2. And so as that happens, we get exactly the same picture as before. The range of common rates shrinks, the range of secret rates increases. Okay, so it looks just like the Gaussian case, except that now we have the case, you see the red line here, is the case where sigma 2 is 1. So the fading parameter on the secondary link is the same as the fading parameter on the primary link. So the two links are statistically identical. But yet we still have, so there's no degradedness now, but we still have a healthy perfect secrecy capacity region. So even without degradedness, if we have fading, we can transmit with perfect secrecy using the physical layer. All right, well, I don't want to spend a lot more time on this, but let me just tell you what's happening here. So what's happening here is that just like in the case of multiple antenna systems, we're taking advantage of the fact that the fading fluctuates randomly. So there'll be times when receiver 1, even if receiver 1 has a more intense fading, there will be times, infinitely often, that receiver 1 has a better channel or a better look at the source than receiver 2 does. And in that case, we're in Weiner's degradedness situation. So we can transmit secret message and the common message at the same time. When the fading fluctuates again and receiver 1 is worse than receiver 2, we don't want to transmit the secret message. We'll transmit only the common message. We'll take advantage of that capacity to send the common message. So in that way, we're able to transmit the secret message and the common message. And it doesn't really matter what the intensity of the fading is. It just matters that it's fluctuating. Okay, well this is, wireless networking is a lot like organic chemistry. In organic chemistry, you study the bonds, right? And then when you understand the bonds, you think you can understand the molecule, right? Well, in networking, we like to understand these little networks, the broadcast channel, okay? And then we put them all together and we understand the big network. So some of the other important channels are the multiple access channel, where you have multiple transmitters in a single receiver. This problem has also been considered in the same context. And again, this is with Ying-Bin for the Gaussian case, and then with Ying-Bin and Ruheng Liu, another former postdoc of mine who's at Bell Labs now, for the fading case. We've also looked at the interference channel. This is with some colleagues at Princeton, including Ann Shlomo and Ying-Bin. And with other colleagues, this is Hesham El-Gamal at Ohio State, where we've looked at a problem called interference alignment in this context. So the interference channel is a channel with multiple transmitters and multiple receivers. Okay, so now you have interference in the network. Another important class of channels are the relay channels, which are channels where there's another terminal in the network. So it's a three-terminal network: source, receiver, and a relay. This is an important class of channels for emerging standards. We've also looked at this channel, both for the case where the relay is a friendly relay and for the case where you want to keep the message secret from the relay, but you also want the relay to help you relay your message. So there are various variations. A very interesting channel here is the so-called MIMO channel. That is the one where we have multiple antennas in addition to all these other things. And there it turns out that we get, with multiple antennas, we get additional degrees of freedom that allow us to get rid of completely the issue of degradedness. That is, we can transmit, even without fading, we can transmit to multiple terminals in perfect secrecy when we have MIMO transmission. So there are a lot of interesting things here. I don't really have time to go into them all, but I'll just mention that this is a very rich area of research. It basically connects to all other areas of, a lot of other areas of communications, coding theory, design of codes to achieve particular objectives, networking, interaction between the network and the physical layer, game theory. This is an adversarial problem, so there's a game theoretic way of looking at it from a game theoretic point of view. And also a relationship to cryptography. You can think about using techniques that combine physical layer security with traditional encryption. So you maybe use the physical layer security to do key management, for example, and then use traditional encryption for information-bearing messages. I don't have time. I'm sort of going a little slower than I expected, so I don't have time to talk much more about this, but I'll just mention, and hopefully these slides will be available somewhere. There's some books on this subject if you're interested in learning more. Okay, well, let me talk now, shift gears completely and talk about another problem, which is distributed inference or distributed learning, which is motivated by the application of inference in wireless sensor networks. And I'll say a bit more about that in a minute. But this is joint work with another colleague, Sanj Kulkarni at Princeton, and one of our former PhD students, Joel Pred, who's now at the RAND Corporation. So a sensor network is a network of sensors, and it's well named. And typically these sensors are put out in places where people don't want to go. Okay? So you might think about, say, a field where you want to do temperature sensing or seismic sensing or chemical sensing, and you fly over and you drop sensors out. They start taking measurements, and then somehow they're going to have to make inferences about what's happening, say, with the temperature or the seismic activity or what have you in that area. Because these sensors are typically put in places where people don't want to go, they're very energy limited. They're severely energy limited because you can't go out there and change the batteries on them very often. So for that reason, we can think about a sensor network as being a network of devices that can communicate best only locally. That is, wireless communications takes a lot of power if you try to transmit over a long range, but to transmit short range is relatively low power, requires relatively low power. So it's of interest to look in such networks at techniques for doing inference that involve only local communication. Okay, and I'm going to speed up a little bit here just because of the time. But one of the ways, so that basically what that does is the radio topology here, that is the radio range of various sensors, creates sort of a graph of connectivity that we can use, or that we need to observe when we're doing computations in the network. Computations meaning taking the data and trying to do computations on it to make inferences about the physical surroundings. So one way to model that is as a so-called bipartite graph, where one set of vertices of the graph correspond to the sensors, or more generally to a set of learning agents, and the other set of vertices corresponding to the data that we take. In the case of learning, this is a training database. And then we have an edge between a vertex up here and a vertex down here. If that sensor can see that piece of data, okay? I mean, and for example, in the sensor network case, the data reside at the sensors, and the sensors can see the data of their neighboring sensors, okay, because they can communicate locally. So that sets up a graph, and it describes the data that can be accessed by various learning agents or sensors. So one way to observe this graph is to let each sensor make inferences as if the data it could see were all the data there are. Okay, so this is so-called local learning, where each sensor looks at the data points of its own data points and those of its neighboring sensors and makes some inferences about the environment. This is called local learning. It's got the advantage of being local. You don't have to do any long-range communications with this scheme. But it has a problem called incoherence, which means that two sensors that share a data point, like in this case you see F1 and the last sensor share this data point, they have other data points which are not in common. So they're going to make different inferences about that point, which means that the inferences made by these learning agents or sensors are not coherent. So this is a problem called incoherence, which is provably bad. That is, you can show, there are theorems about this, you can show that incoherence is bad for inference. You can always do better if you have than you do with incoherence. So another way to solve this problem, which is joint work with Joel and Sanj, is to do what's called message passing. That is, we can take the same graph, let the sensors do the same local learning, but as they learn, or as they make inferences, they can pass their inferences back down into the database. That is, they can share their inferences with their neighbors. And if we go in sequence, go through the sensors in sequence, doing local learning, sharing with the neighbors, moving on, and cycle through this multiple times, it turns out that we get an algorithm that, first of all, is coherent. It doesn't have this problem of incoherence, but also it converges to something that's optimal for this graph structure. Okay, so by using message passing, we can get a type of optimality, we can get coherence, and we can still maintain the advantage of local-only communication. And just to show you an example here, this is just an example, very simple example, where the sensors are randomly placed along a line between -1 and 1. They're observing a function plus noise. They're doing so-called kernel regression. And two sensors are neighbors if they're within R apart. Okay, if the distance between them is less than R. And what this shows is the error of learning, the mean squared error, versus the radius of the neighborhoods. Okay, the solid line at the bottom, which looks almost like 0, is for centralized learning, where you take all the sensors' data together and do kernel regression. The dotted line at the top is for local only, where you do local learning without message passing. And you can see here that the radius of neighborhoods has to be very high. You almost get the entire interval before you get decent performance. But with message passing, even with radius of only 0.2, this one is message passing, the dashed dotted line, we can get performance very close to centralized regression. So just mention a couple of other works here. I don't have time really to go into a lot of depth here, but I'll mention another problem which might be interesting to some of you, which is the problem of judgment aggregation, which is a problem that comes up in psychology. And this is work we did with Dan Osherson, who's a psychologist at Princeton. And this has to do with this problem of incoherence again. So usually when you have human judges making judgments, they're not coherent in a certain way, okay? Meaning that the things that, if you try to put them all together, you'll get something that doesn't necessarily make sense, okay? Because there's all kinds of human factors. So judgment aggregation is a way of putting human judges, taking the judgments of human judges and putting them into a coherent form. And we've used some of the same ideas in that problem, which is a totally different problem, but mathematically a very similar one. And there's a couple of papers on this, and we've written another paper recently using predictions of presidential election data that we took at the last presidential election that also looks at this idea there. When you're doing polling, how do you combine the results of polls coherently? All right, well, there's a lot of interesting stuff in this area, but I want to move on because I'm getting low on time. And the next area I want to talk about, and I was talking about this with some of the students earlier today, this has to do with the problem of finite block length capacity. This is motivated by the problem of multimedia information transmission. And this is joint work with another colleague, Sergio Verdu, and our former student, Yuri Polyansky, who's now at MIT. So this is this sort of addresses the most fundamental problem in communication, which is sort of illustrated here. You have a source which takes one of m possible values, call it W. We want to send it through a channel, okay? And we do that by first encoding the source into a code word of length n, where n means we're going to use the channel n times to send the source. The channel has noise and fading and so forth in it, so that converts the channel input into the channel output, which is a corrupted version of it, also of length n. And then there's a decoder which tries to take those outputs and recreate the source. W hat is an estimate of the source, and that's really what communication is about, at least at the technical level. So in this setting, we're interested in so-called n-m epsilon codes. So an n-m epsilon code is a code that takes a source with m possible, that can take one of m possible values, encodes it into n channel uses in such a way that the decoder can decode the code word with probability of block error less than epsilon. Okay, so that's an n-m epsilon code. And a very fundamental quantity in communications and information theory is the maximum m for which there's an n-m epsilon code. So for a given block length and block error probability, what's the most bits you can send across the channel? So log 2 of m is the number of bits in that message. Classical problem of Shannon, or classical result of Claude Shannon, is that if we let the block length go to infinity and the error probability go to 0, log of this number divided by the block length goes to a fixed number which is called the channel capacity. So it's the Shannon capacity. It's a very fundamental result in information theory, and this idea of channel having a capacity really drives a lot of technological development in communications. This is a beautiful result, but it has a couple of flaws for certain types of communication. So in many applications, particularly multimedia transmission, the block length is typically finite because, for example, in speech transmission, you can't wait forever for the message to get across. You have a delay constraint. And also the block error probability doesn't have to be 0. That is, you can make a lot of errors in speech or video transmission and the perception is the same as if you didn't make the errors. So we really need to refine this result for cases where the block length is not finite and the probability of error is not 0. So I think I'll just get to the punchline here just to save time. It turns out, and this is a work that was in Yuri's PhD dissertation, that we can refine Shannon's result in this way by adding an extra term in an expansion of the quantity m star in the block length n. And this is what it is. So we know that the leading term is a function of n has to be linear in the capacity c, because if we divide by n, let n go to infinity, then we get c. The next term, turns out, is a root n term, and it involves the tail of the unit Gaussian distribution q, the inverse of that, evaluated at the block error probability, and another quantity, v, which we call the dispersion. Okay? Now the dispersion, so the capacity characterizes the asymptotic information carrying capability of the channel. The dispersion tells us something about how it varies for finite block length and finite error probability. And for those of you who know your information theory, the capacity is the expected value or mean of a random variable, so-called information density, and the dispersion is the variance of that same random variable. So we can compute the dispersion in much the same way we can compute the capacity. And this just shows for the additive white Gaussian noise case and a particular parameters how well this approximation works. This is the block length. This is log m star over n. This is the capacity in the limit. There's the Shannon capacity up there. And then the red line is an upper bound on this number, the so-called converse bound. The blue line is an achievability bound. It's a lower bound on the number that we're looking for. And the approximation that I gave you is shown in this dashed line. And you can see that for this case, it's right in there. First of all, the upper bound and lower bound are very tight. This lower bound, by the way, is also part of Uri's dissertation. The upper bound comes from Shannon. And, but you can see that this approximation is very, very close to these two bounds. So it gives us a very good idea of what the actual capacity is for finite block length and finite error probability. And there are a lot of other examples. This is just one, and they all look like this. So that allows us to now look for finite block length, to look at fundamental limits on communication, just like we do for infinite block length with Shannon capacity. And due to in the interest of time, I'm not going to go through this, but we've done some computations. This is joint work with Tom Richardson at Qualcomm on some practical codes and how close they come for finite block length. We also can look at certain types of protocols, optimize them over block length and so forth. And so it gives us really sort of an information theory for finite block length, which we can then now use the power of information theory in problems like multimedia transmission, where we do have noticeably finite block length and error probability. All right, so let me just spend a couple of minutes on this last problem, and then I'll take questions, and I'm about out of time anyway. So the last problem I want to look at is the problem of message delivery in small world networks. And this is motivated, as I said earlier, by the problem of social networking. This is joint work with another colleague, Meng Chang at Princeton, and one of our former postdocs, Hazer and Altikin, who is at Melbourne University. And this sort of work addresses the problem that's a sort of a classic problem in social psychology, which is the small world problem. Many of you may be, there's a folk theorem that any two people on the planet are separated by 6 degrees of separation, right? There's even a play, right, to that name. And Stanley Milgram, a social psychologist in the 1960s, set out to prove that theorem by experiment. And he did an experiment using the postal system where he basically did show that the expected numbers of degrees of separation between two people randomly chosen sort of in Kansas and Boston was 6. Okay. So there's been a lot of criticism of this work as scientific work, but on the other hand, and there's been a lot of repetitions using the internet and other things. But the two important conclusions that came out of Milgram's experiments, which have held up, are, first of all, people are connected through relatively short chains of acquaintances. That is, there is a surprisingly small degree of separation between most people. And secondly, you don't need to know the whole graph of connections to find those. You can find them using local information, or what in communications we call that, say, local routing, okay? And it turns out we can explain this using some analysis, and I think given the time, I'll be very quick here. We can set up a model for the world. Maybe it's a Tom Friedman model because it's flat. And we can distribute people at random and come up with a model that involves short-range communication and long-range communication with local routing. And we can ask questions about the average delivery, the average number of hops it takes to get a message from a randomly chosen source to a randomly chosen target. And I won't bother you with details here. This is a model that comes both from the social science community and from the electronic communications community, so it's a pretty good model. And from this model, we can develop actually formula for the average number of degrees of separation. And if we compute with this formula for various size networks, we do find basically what Milgram found in his postal experiments, that the number of degrees of separation for small social distances, or for small distances, in whatever metric, is linear in the number of, in the distance between the target and source, okay? But after a while, this saturates. So this saturation is the sort of the number of degrees of separation. It's like 6 in the folk theory. And we, in fact, see this for all size networks and all different kinds of topologies. And it's also borne out by other more recent social experiments in the social sciences that have noticed not only the saturation of the degrees of separation, but also this phenomenon here. So this sort of is a mathematical model for what's going on in these experiments. We can look at other topologies. It doesn't really depend on the so-called flat Earth topology. We can look at the circle, the sphere, which looks more like the real Earth, and so forth. You can ignore the formulas, but we get the same basic type phenomena. So, and this can be generalized to other topologies, other connection models, and a lot of other types of things. Some social phenomena can be explained using this model, at least, from a high level. And so I'll just point you to 2 papers, both with Hazer and Meng. One appeared last year in the Information Theory Transactions, and one, which is a bit more experimental, is appearing in the Journal of Mass Sociology early next year. This is an example of a more general class of problems that relate the virtual world of social networking to the physical world of real networking, or of computer and communication networking. We're used to working in this model in this world as engineers, where connections are based on wireless links or fiber optic links or what have you. But up here, links are based on things like friendship, kinship, trust, and so forth. And in fact, this kind of network drives most of the traffic in the physical networks. So it's important, I think, for engineers to understand how this kind of virtual network should affect the physical networks that we design. So I think, given time, I'm going to stop here. Unfortunately, this is my last slide. These are the 4 things I talked about: physical layer security and wireless networks, motivated by secure information transmission; distributed learning, motivated by inference and sensor networks; finite block length capacity, motivated by multimedia information transmission; and finally, message delivery and small world networks, motivated by social networking. And with that, I'm happy to take questions. Thank you. Yeah, Gonzalo.
Vince, the distributed learning message passing algorithm is very interesting. It reminds me of turbo coding in
Yes.
Eric codes a while ago.
Yes.
You start passing information from different decision points.
Yes. So the question, I guess, is how does this relate to turbo codes or the decoding of LDPC codes, linear low-density parity check codes? Well, very much. I mean, once you see a bipartite graph and you'd like to make some decisions about things there, you start thinking about message passing, because in another great invention of the 1990s was turbo codes, which actually allows one to represent codes something like this and use message passing with discrete arithmetic, not inferential statistical inference type arithmetic to make inferences. But in fact, it's suggestive of this, and that's partly how we got to this point. Once we realized there was this bipartite graph structure, the next thing we thought of was message passing. So that's not too surprising if you look at that path. So good point. Other, yeah. Charlie.
About the cryptography of the security part.
Mm-hmm.
Shannon proved theorems that says information theory gives us provably secure systems.
Yes.
But as a practical matter, those theorems haven't proven too useful. And almost all our encryption is based on computational complexity.
Yes.
Do you think that will change with this network?
Excellent question. So, in general, to have to communicate securely, there has the receiver that you're transmitting to has to have an advantage over any eavesdropper. In a traditional encryption system, it's knowledge of the secret key, or not really, because the secret key is not really, typically the key is formed by expanding a crypto variable, so it's not really, doesn't have this property. So you hope that there's some computational difficulty in breaking the code. So public key cryptography is based on the difficulty of factoring the products of primes, right? So that's what that's based on. So it's not provably secure, but people trust it because nobody, you know, you can just make the primes bigger and bigger and bigger and bigger, and you know that the computational problem is harder and harder and harder. So here the advantage you're taking advantage of is a physical advantage, okay? So it also is not perfect because, you know, you're relying on fading and other physical properties. So I think my best feeling about where this is useful is not going to be in applications like banking or military applications where you have to have absolute security. There I think you want to use encryption. You know, so if you're going to say attack at dawn over your network, you want to be sure it's encrypted very securely. On the other hand, if you're a content distributor like a cable television station and you have content, some of which is multicast, you know, basic cable, and other which is premium, you might think about using some kind of physical security to provide protection for the premium content. Because you don't have to be perfectly secure. You just have to disrupt it enough to make it annoying so that people won't steal the content, right? So I would say that if there's a niche application for this kind of thing, it's places where you want to have enough security to disrupt eavesdroppers, not necessarily enough to be completely sub rosa, right? So sensor networks are another example, right? You know, you would like to protect the sensor data, but it's much more important that your batteries last, and so you don't want to have public key cryptography going on all the time in these terminals. So I think there's always going to be a place for the hard computational type of cryptography, and that's going to be, you know, the Swiss banks and the, you know, military applications. And then but then there are going to be other applications where you really can sort of use this kind of security, and I think that's where we're going to see the first applications of this. It's a great thing to think about, though. Good question.
So, if I may, related to this one, have people developed codes to try to achieve the limits that
yes.
we were discussing, and how close are
yes.
to the limits?
For the wiretap channel, there are codes. The theorems are based on very impractical things, as you might imagine, random codes and typical set decoding. But you can emulate that using LDPC codes or families of coset, linear coset codes. So there are codes that can be used for this. Yeah, they're fairly recent. I mean, the papers are, some of them are still being reviewed and so forth. But there is work in that area. So this area is now turning to that aspect of development. That is, we know there's some capacity out there. Now, how can we exploit it? And that involves codes, you know, networking issues, and other things.
Any more questions?
Okay.
Thank you very much.
Thank you all. Thanks for coming.